Welcome all of you to my presentation for the 21st IEEE International Conference on Nanotechnology. I am Venkatramesh Naganboina, research scholar from IIT Hyderabad, India. I would like to present our research work entitled Fabrication of Highly Selective NO2 Gas Sensor for Low ppm Detection. As we know, over the past few years, air pollution is a global environmental problem and it occurs due to transportation, agricultural activities and industries. However, all these sources releases various toxic gases and all these toxic gases are most dangerous pollutants to human health and environment. Certainly, it is estimated that air pollution caused over 3.4 million deaths worldwide and above 1.2 million deaths only in India. This figure indicates that there is a system to monitor the air pollutants for the safety of human health and environment. So that's why herein we are choosing nitrogen dioxide gas, detecting nitrogen dioxide, because nitrogen dioxide is a highly notorious red-brown oxidizing gas with pungent odor. It is the major source to cause acid rain and ozone formation. So inhalation of nitrogen dioxide causes either in short-term or long-term health effects. Short-term health effects is like dizziness, unconscious, headache, etc. Long-term health effects is like it affects human health either in bronchitis and asthma, and it may lead to respiratory disorder and reduce lung function. According to ACGH, threshold limit value of nitrogen dioxide NO2 is 3 ppm for 8 hours and 5 ppm for 15 minutes time weighted average. In this regard, to detect nitrogen dioxide, literature is happening using metal oxide based gas sensor. It has various advantages such as high response and selectivity, good absorption and desorption kinetics, but it has disadvantages, high limit of detection, higher operating temperature. Therefore, due to this high limit of detection and higher operating temperature, there is a need to detect low concentration of target gas at low working temperature. That's why herein we choose this research gap as a problem statement, that is efficient detection of low concentration of nitrogen dioxide gas at low working temperature. In this regard, researchers are looking for other alternative materials such as TMDs, transition metal dichalcogenates. Why transition metal dichalcogenates? Because it has versatile chemistry, excellent semiconducting properties, and it has ultra high surface to volume ratio with tunable band gap. So there are various types of TMDs, that is such as tin disulfide, molybdenum disulfide, tungsten sulfide, iron sulfide, etc. However, now we have chosen here in tin disulfide because it has larger electronegativity, moderate band gap, and tin has unpaired outermost 5p electrons. It offers favorable gas sensing for the target gas. That's why herein we choose a tin disulfide. So now we synthesize the tin disulfide using one-step hydrothermal method. Herein tin chloride pentahydride used as a tin source, thiourea is used as a sulfur source. So sodium disulfide is used as a stabilizer. After forming homogeneous solution, we transfer to 50 ml autoclave and kept at 180 degrees Celsius for 12 hours. After coming to room temperature naturally, we centrifuge using DI water and ethanol multiple times to remove impurities, and then dried at 70 degrees Celsius and calcinated at 300 degrees for 3 hours in argon gas ambient. After synthesizing this tin disulfide, now we characterize using XRD spectroscopy to confirm the material formation tin disulfide. Here in figure 2a displays XRD spectrum. It has various diffraction planes, and all these diffraction planes are attributed to tin disulfide hexagonal structure with its respective lattice constant. Next, if you see all these diffraction planes are well matched with the ICDD card number 657657. Additionally, we have performed Raman spectroscopy as also. It exhibited two peaks, one strong at 310 centimeter, another at 210 centimeter inverse. These two peaks are well matched with the literature. Now, after synthesizing this tin disulfide, next characterization, now we fabricated chemiresistive gas sensor. Prior to fabricate chemiresistive gas sensor, first we patterned a gold interdistillated electrode pattern on glass substrate. Initially, we took glass substrate and cleaned with piranha solution and DI water. Then we deposited 20 nanometer titanium layer using electron beam evaporator. Subsequently, we deposited 100 nanometer gold layer on top of titanium. Herein, titanium is used as an adhesion layer. Then we spin coated positive photoresist. After that, we wrote mask pattern using laser writer and photoresist. Then we developed the using developer MF39, and then using standard wet metal etchants, we etched the gold and titanium layers. And finally, we cleaned using organic contaminants with acetone and DA water. And at the end, now we fabricated chemiresistive gas sensor by drop casting 10 microliter of the tin disulfide on IDE pattern and kept at 70 degrees Celsius for 2 hours to evaporate the solvent completely. So this is the step-by-step procedure of fabricating chemiresistive gas sensor. So after completing this fabrication of chemiresistive gas sensor, now we performed gas sensing experiments using our laboratory gas sensing setup. This is the diagram of gas sensing measurement system in our laboratory. Now we have performed gas sensing performance at different temperatures towards different gases. Why we are using different temperatures? Because tin disulfide has a moderate band gap around 2.3 electron volt. That means it offers high resistance at room temperature, unable to measure with source meter. So that's why you increase the temperature beyond 50. From 60 degrees Celsius onwards, it offered measurable resistance with the source meter. Now we performed gas sensing performance at different temperatures, that is 60, 100, 150, 200, 250 towards different gases. However, this sensor exhibited maximum response towards nitrogen dioxide towards nitrogen dioxide for 1.5 ppm, and it exhibited minimal response towards all other gases. So that means this sensor is highly selective towards nitrogen dioxide at an optimized temperature of 100 degrees Celsius. This might be attributed to strong binding energy between SNH2 sensing material and nitrogen dioxide gas. So this figure concludes that since tin disulfide as fabricated sensor is exhibited superior selectivity towards nitrogen dioxide at an optimum temperature of 100 degrees Celsius. So now we will look into it, what type of sensing mechanism might be plausible in this sensor. So it can be explained now using energy band diagram. So initially we exposed synthetic air onto the sensor. Synthetic air has an oxygen molecule. It accepts an electron due to its electrophilic nature and forms chemisorphed oxygen ion O2-. Due to this, space charge layer widens, potential barrier height increases. Therefore, charge carrier concentration in the SNH2 decreases, conductivity decreases, hence resistance of the sensor increases. Subsequently, we expose the nitrogen dioxide onto the sensor. It has a property oxidizing nature. It accepts an electron and reacts with pre-chemisorphed oxygen ion and forms NO2- and 2O-. Hence, widens the space charge layer and increment in potential barrier height. Therefore, charge carrier concentration in the sensor decreases further, conductivity decreases, and thereby increment in resistance further in contrast to resistance of the sensor in presence of oxygen or synthetic air. So this might be the plausible sensing mechanism happening in SNH2 sensor. Now we will explain the sensing performance towards nitrogen dioxide at different concentrations. So now we purged different concentrations from 1.5 to 6 ppm of nitrogen dioxide. It exhibited stable response and recovery characteristics with small baseline drift. It could be attributed to partial recovery. After that, we calculated response using this equation and fitted the mathematical equation between response and concentration. Power law was fitted and it exhibited slope around 4.42% per ppm at a concentration of 1.5. Additionally, we calculated response time from this transient characteristic. It exhibited it displayed response time 6.8 to 9.5 for the concentration 1.5 to 6 ppm. This promises it can be suitable to monitor the real-time application. Furthermore, to see the accuracy of the sensor, we performed repeatability test by purging 1.5 ppm of nitrogen dioxide 4 consecutive cycles. So it offered promising characteristics with small baseline drift. It can be eliminated using signal processing techniques. So now we will conclude this talk by giving summary of our research work. Initially, we synthesized SNH2, then we characterized using XRD and Raman spectroscopy. After that, fabricated using drop casting technique. Then selectively optimized temperature and target gas for this fabricated sensor. Then we performed gas sensing performance at an optimized temperature 100 degrees Celsius. Finally, I am concluding. Before concluding, in future we would like to work on how humidity is affecting on the sensor response, and at the end we are planned to make a prototype device for monitoring the real-time application. Thank you for your attention. I am ready to take further questions. Thank you.